Yeah, how about you?
Pretty good. Trying to get back into the groove.
Yeah.
Is the Vesper handout the same one that we got last time?
Yeah.
Do you need all three? Once he gets here, 30 minutes. In the back.
All right, let's go ahead and get started. So, of course, welcome back, those of you that have survived. And so, right with that, we kind of shrank to a smaller room, so now we're all fit in here. So that's kind of nice. And I'm still streaming my lectures to YouTube, so you'll still have that available. I'll post the link. I think I forgot to do that, so those few of you who don't know me from last quarter, I apologize for not letting y'all know the insight information. All right, let's do roll call before I forget, even though, again, I know most faces. And then those of you that I don't know, feel free to correct me on your name, or if I know you and I still screwed up your name, please let me know. All right, Tyler Bates, where are you? There you are. Jens, where are you sitting? Is Jens here? No? Okay, Phoenix, I see you. Andrew, over there. Rebecca, Logan, Cabrina, Saeed, Cora, I like your hair. Audrey, you. Shane, welcome. Peyton, yeah. Misach, is he here? I don't see him. He didn't make it in yet. Savannah, Riley, Jonathan, Eugene, where are you at? And Trenton, welcome. Nice. Madden, Matthew, Keller, and then Smith, I'll mark you off. And Carmen isn't here yet. I assume she'll be straggling. Breja, Aliro, Tori. Let's see. Oh, there's Misach. Welcome back. Angel, is he here? Let's see. Angel. Michaela, welcome. Camilo. And Christy. All right, was there anybody that I didn't call that wants to sign up for CHEM 222? All right, I think we have everybody, other than a few stragglers. And so we'll just go over the course, even though it should be pretty similar to last year. I can log in. So just like I did last year, I'll have the printouts of your homework and lab available. And then you can also turn them in online, but you don't have to. I'll take everything by paper copy. And so here's just the Blackboard in case you haven't seen it. So of course the syllabus. And again, pretty standard. So we have that information. I separated out the labs so you can have all the labs there so they're all available. And then I'll open up, of course, the week by week. And so just like last year, I have the notes, recitation has all the homework answers, and then just have all the assignments there. Oh, and don't forget, while we're in here, don't forget your reading questions. So they're only worth like 10% of your grade, but that 10% adds up by the end. So that can be the difference between passing and failing. So definitely don't forget your reading questions. And then I just have old archives as well for you to look at. Any questions just about the general structure of the class? And then we'll have our quiz. So again, those of you who haven't had me, we'll have our quiz on Thursdays during like that recitation period time. So just like before, and the recitation will be in here as well. Okay. So let's see, I'll probably talk about your paper more on Thursday because that's kind of coming up on the horizon. So I think we have it by week 2. I want you to select like a topic officially, and hopefully you started thinking about it fall term and maybe thought about it over the break, maybe not. But we'll go over that on Thursday. So let's talk about other things. Hang on. So I think everyone signed up for lab lecture recitation, but I'll just make that announcement. Sorry. Why is it that when you come back from break, there we go. Sorry, my mapping had changed. All right, so make sure you're registered for all 3 sections. So lab, lecture, recitation. Again, I think everybody is. I was checking my rosters and all the numbers add up, but again, just double check that on your end. So I won't put out the codes. But. All right, and then I also mentioned last quarter that we were going to have a volunteer opportunity, extra credit opportunity coming up. So I'm probably going to offer 10 points for this because it's a large volunteer. And there'll be other extra credit opportunities in case you have work. And so let me pull up what we're doing. And so I have some of my Earth Club members in here as well, but we're hosting it, so it's Earth Club, Engineering Club, and the Honors Club, so Alpha Zeta Phi, and we are holding a Science Expo at RCC, so it's going to be in about 2 weeks, so Friday, January 19th, so not this Friday, but the next Friday, and so I'm looking for volunteers from class to kind of help lead the experiment, so I have kind of, behind the scenes a list of potential demos that we can do, and then I just need, people to help run them and help facilitate the event. So if you can volunteer, that would be amazing, and then like I said, you'll get 10 points probably on a midterm is where those would go. And also spread the word so I can email this out or post this as an announcement, but invite the community, invite all your friends, and it's open to all ages, so we'll have kind of, a range of activities. And of course, depending on your age, they'll get different things out of it. So really great opportunity. do it for the extra credit, do it for the resume, so that's a good opportunity to talk about, hey, I volunteered and I was teaching and leading in the community, so that's really good to put on the resume. So extra credit or science expo. And so just either email me or talk to me after class or during lab, and then we'll get you signed up. And then probably you're going to have a meeting this Friday. And if you can come, that'd be great, at like 2 p.m., just so we can go over the demos and experiments. So in case anyone needs to practice, then we can go through the demos and so you feel really comfortable for leading them. But a lot of them are easy, like slime, Newtonian fluids type of thing, or things that we've done before, like maybe doing the flame test for people. So that's always really popular, but we need somebody to lead it because we can't have, people doing their own flame test for safety. So that's where y'all come in. All right. Any other announcements that I've forgotten or questions? And then we will have lab this week. So lab starts. So that's on our syllabus. So we'll have check-in, and then you can grab the lab. So the lab is mainly a computer-based lab. So that's fine if you didn't wear, your safety closed-toed shoes today. It's mainly computer/modeling. All right, I guess let's dive into lecture then, unless I'm missing anything. And so I have up at the front the Vesper handout, so you may have it from last quarter. Also, that's another thing, I didn't print out new periodic tables, but you can bug me in lab and I'll print out fresh ones if you need on the cardstock. Otherwise, if you want to hang on to it, hang on to it. It's got all your notes, but if you need a fresh start, let me know as well. All right, so we're going to go through this. In last quarter, we kind of talked about, drawing structures, and we practiced that a little bit. But now we're going to kind of go back, redraw these structures, get the geometry down a little better. So we didn't really cover geometry that well last quarter. And then we're also going to take a look at the orbitals. So really now getting into, what molecular orbitals are coming together to make these different compounds. And so this is a really nice, handy cheat sheet, I would say. And so we're going to be walking through examples of all of these and looking at that. So let's start with, we'll start with our group 2. And so another useful resource is I put a link to the Vesper theory page for Wikipedia. So this is really nice. Again, Wikipedia shouldn't be used for history or current events or anything, but does a pretty decent job with science. And so this is also giving the same information as the sheet we're looking at. So whatever format, feels good to you. I think the book also has similar charts. And so we're starting with this, they call it steric number. And if we go back to our sheet here, it says electron pairs, but basically how many things are attached. And we said that that was either electrons, so either lone pairs or atoms. So how many things were attached to it. And so let's start with our linear example. And can anyone name maybe a classic example? There's 2 good classic examples. Yeah, so CO2, so water we want to save. So CO2. And let's actually look at CO2. So this is a good one to start off with. So kind of a warm-up. See if you can draw your Lewis dot structure for CO2. What does it look like? What do we remember from last quarter? Gonna get the cobwebs cleared out. So the definition was how many things attached to it. So either lone pairs or atoms, yeah. Does anybody want to put CO2 on the board? Let me see. I'll mark this questionable. Here, Blair, I don't know if you want to use that one. I might grab another one.
Oh, we'll see if this one is. Well, is this relatively visible?
I can see it.
So, I guess to start off, we could take the valence electrons for each of the atoms we have. Oxygen has, I believe, 6 valence electrons, and carbon has 4 valence electrons. And therefore, keeping both octet rule as well as the formal charge, and this works pretty well. There's 4 bonds, which turns it out atoms, 4 valence electrons are this subtract formal charge is 0. And then, of course, for this, there's 4 electrons and then 2 bonds making a formal charge of 6, which matches the valence electrons for both of the oxygens. That's formal charge of 0, and then octet rule says that.
That looks good. All right. And so I'm just going to put, so we have an AX2 structure just following the language of our Vesper. And so what's another AX2 example? So I want to put both of these up, and then we'll kind of go into the details. Any guesses? Do we remember? So I'll give it to you. So it's kind of a funny one. So it's beryllium chloride. And so it's kind of unexpected, right? We might expect it to be an ionic compound, but really it behaves more like a covalent compound. And so it's kind of interesting. And so for our purposes, we generally say that it has a linear structure. And so more correctly, this would be in the gas phase where this is observed. And so again, this is kind of interesting. Let me pull up the textbook or the reference. And so this is just showing you, unfortunately the quality isn't that great of this copy, but it's showing the 2 structures that beryllium chloride follows. And so again, just based off of the basic formula and our Vesper kind of cheat sheet, we'll mainly assume it has a linear geometry, and it is found in the gas state. However, they also found in the gas state that it can do these funny bridging structures. And so we can kind of go back and talk about the differences once we go into that. And of course, you can probably also guess why it's going to do a number of funny things like that. So, right, beryllium wants to be satisfied by the octet rule. And of course here, right, it's only feeling 4 electrons. So a little deficient there. So it does make other structures. And then also in the solid state, it can make a more tetrahedral looking structure where again, they're still in this 1:2 ratio of beryllium to chloride. But of course, right, it's probably trying to satisfy its octet rule by making that structure in the solid state. So that's kind of interesting. And this goes to highlight why it's also important to study things in different phases and why we specify whether it's in the gas phase or solid state phase. And we can only know so much. And so this is, AX2, we can say that it's linear. And now we want to look into some more things. So now we want to say what orbitals are involved. And so now we're looking at our beryllium here. And so let's kind of think about this for a second. So now let's kind of go back and let's remind ourselves. So we have s orbitals. We have our 3 p orbitals. So pz, px, py. Oops. And so you'll note sometimes, again, it just depends where you define your axis. So generally, PZ is the highest principal rotation axis. So I might change which way I call PZ depending on the molecule. So highest principal rotation axes. And so now we're kind of thinking, well, what is its hybridization? So what orbitals came together? And so looking at this, so how might these bond with one another? What orbitals are kind of in the right orientation to make the single bond? Because now we're trying to ask, and we're looking at the difference between these, right? So they're both linear, but now we're looking at, well, this one only has one line drawn. This one has 2. So what does that really mean? What orbitals go into this?
It's possible that for the beryllium and beryllium chloride, it only bonded using the X or Y orbital, depending on what it's looking like. Or maybe that's just S, I'm not sure. But it kind of looks like it's in a line with the P orbital would be in that.
Yeah, so you actually have the right idea that it's kind of both. So beryllium, so we call this, so you're on the right track. So right, we're thinking about it. We can go back, and again, it depends how we define this. So I'm going to redefine this because this would be our principal rotation, right? You can spin it infinitely since it's linear like that. So this is the principal rotation. So let's call this PZ. And so now we're kind of saying, well, who's in line, right? So we have a big s orbital, and we'll just kind of simplify these chlorines as spheres for now, right? So our ball of chlorine is coming in, and we're asking, well, how is it going to interact with beryllium, right? What orbitals is it using? And the answer, so you were on the right track, is, well, both kind of seem like they're in line, right? So now we're getting to this new concept of hybrid orbitals. And so that's exactly what happens. So our PZ is appropriate, right? It's in the correct space to match with this chlorine ball that's just coming on. But so is our s orbital, right? It's also in the same orientation. And so they come together to make our hybrid orbital. So our kind of sp hybridized. And so now this gives us a clue too. So right, we have 2 things attached to it. And so we kind of need 2 orbitals. So that kind of tells us 2 orbitals come together in our sp hybridized orbital. And so now we can draw this, kind of what's going on more in detail. So we have our beryllium, and it still has, right, it's 2 p orbitals, so py, pz, they're just not interacting with anything. And then we have our sp hybridized orbital then, and then it's going to come and form what we call a sigma bond with our 2 chlorines. So now I'm just drawing the orbitals here, and so we can call this a sigma bond. So both these are sigma bonds, and so a sigma bond just means that they're head to head. So they're like right next to each other, And of course, they would be in phase, so that's what it means by bonding, so in phase, just same shading. All right, so that's what's going on there. And so again, sp hybridize, and we can say, in case, just so it's clear, right? So these are all just sigma bonds. So our single bond, they are sigma bonds. So now let's look at CO2. So kind of what's going on here. And we have several things to look at. So right, we want to look at the hybridization of our carbon, of course. We could start with that. Maybe help ourselves by looking at what happened here with the beryllium. But then we might want to look into the hybridization of these oxygens. So take a moment to look at it. Kind of what do you notice? Maybe even what's the steric number on the oxygen, and that'll give us a clue to what's going on there. So maybe what can we say about the carbon? Let's start with the carbon. What do we think its hybridization is? What does it look like?
I think it's gonna have like 4 lobes of the sp or hybridization orbital.
But it still only has our X2, right? So it only has 2 for the steric on our CO2, right? Even though it has 2 bonds.
Isn't that how it makes the double bond? Is because the 2 on the top also bond together? I don't know, maybe that's what not oxygen.
Yeah, so I think you're kind of right, but it's still sp hybridized, right? So we still have, so based off of this X2, and this kind of helps us, so it's still just sp hybridized, but you are on the right track. So let's think about that, right? So we said for our carbon, so this is for our carbon, so sp hybridized, so this is our S plus, we'll call it Pz. So then it makes that, but then you're right, well, we still have a Py hanging out, or let's call this Px, sorry, Px and Py, so I put Py coming in and out of the plane of the board. So these are not doing anything, right? They're currently what we would call non-bonding. But before we figure out who they could interact with, so now let's take a second, and again, you might want to write sp here. So what was the steric number for oxygen, though? What did you notice about that? How many things are attached to oxygen? I think I saw some fingers with the right answer. Other votes? What do we see on there? How many lone pairs? How many atoms?
Well, there's 2 sets of lone pairs and that's bonded to the carbon, so that'll be a step number.
Exactly, right? So everybody see that? So 1, 2, 3. And the way I kind of drew it, that's already hinting at the hybridization. So because it's steric number 3, then yes, it's actually sp2 hybridized. So right now we have kind of our cheat sheet, 3 orbitals going in, so 1s and our 2 P's for our oxygen. So now this is our oxygen. So it makes this 3-lobed sp2 hybridized orbital. And so this is just kind of a formality. So what went into it? So we can call it, so probably S plus P, trying to be consistent, so PZ plus PY likely went into it. And so that leaves, so this is planar, right? So this is kind of planar right now. So you're imagining, right, CO, well, of course, CO is linear, but then I'm saying it's planar in the sense that the lone pairs are in the plane. And so now we're left with what we've called our PX orbitals. All right, so now we're noticing, okay, well, these are involved in bonding, but I have a PX that's not involved in bonding on my carbon. I have a PX that's also not involved in bonding on my oxygen. And so that could give us a hint where the double bond comes from. And so let's first draw out where our sigma bond is coming. And so let's draw our carbon again with our sp hybridized orbital. And so now it's primed to then hook up with our oxygen. And so drawing our sp2 hybridized orbitals, and so you could kind of draw in the lone pairs again. And so this is forming our bond. So again, right, head-to-head interaction again, so directly. So that's where our sigma bond comes in. And of course it's symmetric, so let me go ahead and draw that same thing. So again, another sp2 hybridized orbital, lone pairs in there, and of course, again, another head-to-head interaction, sigma. And so again, this is explaining just one of these lines, right? So each one of these, or one of these lines corresponds to a sigma bond. So that's where that's coming from. Again, that head-to-head interaction between the sp hybridized orbital of carbon and the sp2 hybridized orbital of oxygen. And so again, like we had kind of noticed, well, we do have these px's, and so they're in phase in the same direction. And so that's left over. So let's go ahead and draw that. I'm trying to put it, what's a good color? And so now, right, we're left with our px, we're calling it. So there's a px still on our carbon. And right, there's still also a py on carbon. It's just not going to be bonding. So you could draw it, so py, but I'll put NB, which stands for non-bonding, right? So it's not interacting with anything. You can imagine in a different scenario, though, that's how you get a triple bond, is by having 2 pi interactions. Just not here, right? We don't have any available on oxygen, so that's what it's dependent on. And then let me draw my other px. And so now we have our pi bond. So our second bond here is a pi. And so that's how it generally works out, right? So your first bond is the head-to-head sigma when you have a single bond, and then your double, your triple bonds are going to have to be pi interactions. So now we're seeing that. And so with pi, again, it's through space. So this is what it means, is it's feeling it through the space here, right? So they're not head-to-head, but they're still in alignment, so they're still in phase. And so again, in phase just means the same shading. So they're all unshaded on the top, shaded on the bottom. So this means that you have your pi bonds. So pi bonds, pi bonds. So all that throughout. And so that corresponds then to your pi bond here. And I kind of went excited, so I was just trying to show that it's through space, right? But this is just one pi bond between our oxygen and carbon. Is that clear? I was just trying to show that it's in phase on both lobes of that p orbital. All right, so how are we feeling on this? So kind of seeing how things interact. And so, right, we're getting a little deeper look at bonding, how things actually form. So, right, we have to have electrons, the appropriate number of electrons, but now we're looking at, right, do we have the correct orbitals that can bond together? Do we have, like our pairs? And so that's what we'll be looking into more this quarter. Questions about AX2 so far? So, as usual, right, always interrupt me for questions. And so we can write on this our cheat sheet here. So we had, 2 electron pairs. So that means it was sp hybridized. So that helps us. And so now let's look at our 3 electron pair group. So we'll start with that. And so now we can say, this is sp2 hybridized when I see these 3 electron pairs. And so let's go over some of the classical examples. So our 3 electron pairs, AX3. Can somebody name maybe some classical examples that we remember from last quarter? So there's a problem with NH3. So NH3, we'll save that for 4 electron pairs, yeah. So it has a lone pair. What else are kind of our classic examples?
It'll just be water.
No, it's still not water. So SO3, that's a good one. So this is a good example. So actually, let's take a second. So can you draw out the Lewis dot structure for SO3? That's a good one to warm up on. Does someone want to throw up SO3 on the board? I think I have a better marker. We could also put on that board or front board, whatever board. Yeah, go for it. Yeah, I think this one's working. Oh, okay.
So I started just finding out how many valence electrons there are. Sulfur and oxygen have both 6, so 6 times 4, 24. And since there's only one sulfur, I put that as a central atom. And started with just single bonds. And then what I did was look at the sulfur atom and look at its formal charge. Sulfur. and I saw that it has 6 valence electrons. So if I wanted to get that to 0, I would have to have 12 bonds. Because you have 12 electrons. 2, 4, 6, 8, 10, 12. And then 6 minus 1 half, 12 minus 0 lone pair, 0. And then I put the remaining valence electrons on the oxygens here. And then I checked the oxygen's normal charge. So it also normally has 6. It's got 2 lone pairs, so that's 4 electrons to take away. And then 1 half of the bonded pairs, and there's 4 bonded, so we do half of that, minus 2. That's 0.
So that looks excellent. So did everybody get this structure? Did anybody get other variations, deviations? So
I did it with 1 less double bond just because I felt 12 was super hypervalent, but maybe that's okay.
yeah, 12's okay for hypervalent, but
For sulfur.
yeah, for sulfur. So this is probably the best structure. So this is a really good example. So again, don't let these double bonds confuse you, right? So this is still just an AX3. And so what's the geometry then? Actually, we'll do 2 terms. So I'll introduce this term of electron geometry, which is kind of what I call the parent. And so what I mean by that is, so right, everything in electron pair 3 would have a trigonal planar electron geometry, so even this structure. And then molecular geometry refers to the actual atoms then. So sometimes they're different. In this case, it would be the same. So what's our electron geometry and molecular geometry?
There'd just be the trigonal planar.
Yep. So trigonal planar for both of those. Excellent. And so again, it's our electron pairs are our steric number that tells us, the hybridization, which of course drives the shape. So all that's useful and related. So this was a good example. What are the other classic examples? Other thoughts? Look at your periodic table. It's a whole group of them. Thoughts? I know you're all gonna know them as soon as I say them. All right, what about these guys? So aluminum, chloride, right, gallium, trichloride, trifluoride, tribromide, whatever. Boron, there's also these weird like triethyl boranes. So all these different families. So right, following that simple AX3 pattern. So notice a lot of these tend to be our group 3. So right, boron, aluminum, gallium. And so these are interesting as well. And so right, looking at, let's just say aluminum chloride, for instance. Again, from our kind of basic knowledge, we might expect this to be an ionic compound, but from its actual behavior, it's really a trigonal planar covalent compound, so it looks something like this. And so all of these also have kind of similar properties, and by that I mean they're all angry and reactive, and so we can probably guess why. So if they're in this trigonal planar form, right, they only have 6 valence electrons, and so for example, aluminum chloride is an angry fuming powder, so you open it, and it's like reacting with the water in the atmosphere to make HCl because it wants to make some oxygen bonds. And so that's nice. And so same thing with, these gallium and boron. So boron trichloride is a nasty, angry, fuming liquid. So that's also reacting with the atmosphere. This the triethyl boranes, so these go up in air, so they flame a nice green. And sometimes people use these boranes to check their glove box atmosphere to see if they spark at all. So then that means that there's obviously oxygen in your glove box, which is not desirable. And so again, right, you can draw all of these. I should have put my lone pairs. But they're all very similar. And so let's see. So we can, of course, look at their bonding. And so in this case, right, our aluminum, again, we said that's going to be sp2 hybridized. And then it'll, of course, bond with our chlorine atomic orbitals. And so in that case, it's just making our sigma bonds. And so we could do the same exercise like we did previously, so going through the orbitals, and so we can kind of go through that and see how these made a double bond. And so what was the hybridization of these oxygens again?
I think it was also sp2.
Yep, so right, so these are all sp2, and so we can draw that. So
That makes sense because they're both in the same element.
yeah, and then they have, right, there are 3 things attached to it. And so this is good basics for OChem too. So if you go on to OChem, just keeping track of orbitals, what orbitals are available, that will help you. Oops, let me move this. I didn't give myself enough room. So there's our sulfur. And I'll use the same color for oxygen. So the reds. And so again, right, we can tell, well, there's our head-to-head interaction again for my 2 sp2 hybridized orbitals. Oh, I don't know why I put a 2 there. So just drawing out, right, our oxygens, bonding, so we can kind of see. And again, seeing the geometry, how everything is pretty planar. And so just like before, so we said, right, we had 2 p orbitals going in, 1 s, but that left us with a lone, what we're calling px, left over on all of these, right? So now we have px, px. And so I'm drawing it on all of them, right, because it's the only one available still. So it's not involved in our hybridization. And so now we can tell, well, this is our pi bond then for our SO3 molecule, and so that explains where a pi bond comes from. Again, that through space interaction, so through space. And so again, right, imagine the sp2 is planar, and then our px's are all sticking out. So that helps. All right. Oh, and then, so I almost forgot about SO2. And so now let's look at, if you remember, so we said we had our classic example of this bent structure, and bent in the sense that it has the parent geometry of trigonal planar. So let's draw that out. I think we've done this before in class, but let's draw it out again. So remind yourself, so what's the Lewis dot structure of SO2? And then we'll look at it. Does someone want to put SO2 on the board somewhere for us?
I can do it.
All right, go for it. And wherever you want to stick it, either under the CO2 or there's
Sure.
cardboard.
So what I did was, well, I came up with two possible ones. First one was just silver, double bonded to both the oxygens. And then the second one was the sulfur with a triple bond to the oxygens. And I'll explain why I did that, because here the sulfur has a +2 formal charge, and here both the oxygens have -1. And I remember you saying that it's better for the charges to be on the plus side, so I thought maybe this, but I'm not sure. Let's see.
I think you're missing the electrons.
There's another electron pair that's going to silver. Oh, here.
Yeah, and then that might help your formal
Oh,
charges.
there we go. Yay!
Yay! So yeah, this should be the best structure, I think. So, and this matches what we're kind of expecting. Not that we should use that, but right, we said, well, it's AX2E is the abbreviation, so meaning 2 atoms, and then the E stands for the lone pair. And so it's still sp2 hybridized, right? So we can see that it's just one orbital, of course, has our lone pair instead of bonding. And then, so this is where we have different electron geometry and molecular geometry. So what was our electron geometry? Do y'all remember? Yeah, so trigonoplanar, since it's still in our parent family, still sp2 hybridized. And what's our molecular geometry then? So bent. And remember, this is the one that sometimes textbooks make the distinction between the two bents, since we'll get to the other water bent. So sometimes this is called V-shaped or like V-shaped bent. So you might see those variations in textbooks since it's a different angle. So this angle is about 119 compared to the 104.5 for the other tetrahedral structure. All right, let's keep going. So now we're at our 4 electron pairs. And so now if we're at 4 electron pairs, let's go back to here. So now we're just kind of following this pattern. And so now if it's 4 electron pairs, that's going to be 4 orbitals combining. So all of these are going to be sp3 hybridized. So I'll go back. So 4 electron pairs, sp3 hybridized. And so thinking about what that looks like, and so it's kind of tetrahedral. I apologize, I'm a terrible artist, so something like that, 4 equal lobes. Again, I can't draw. And so let's see if we can start with our AX4 examples. So what would those be? Have our classical examples.
CH4.
Yeah, so methane, CH4. So this is, right, our standard example of this. And so we can draw this out based on last quarter. And so now this quarter we want to practice our 3D drawings, try to get those better. Right, our wedge for out of the plane, dash behind the plane of the board. And so many other group 4 atoms tend to make the same sorts of compounds. So right, we can do silicon tetrachloride or go crazy. So germanium tetrabromide. etc. And of course, right, all those would be tetrahedral. I'll just draw silicon tetrachloride for fun. And so then so for this one, so what's its electron geometry? So tetrahedral. And then, right, same for its molecular geometry. Tetrahedral. Yeah, so methane would be the same. And so now let's look at our next example in the electron group. So right now we're going from tetrahedral to trigonal pyramidal, or our AX3E examples, which we had said, right, ammonia was a good one. Or other, you know, group 5 with 3 substituents. Oops. So of course, right, pH3 would be the same, or PCl3 would be the same. So those sorts of compounds. And so let's draw phosphorus trichloride. So now, right, our phosphorus is just like nitrogen, so 5 valence electrons. And just drawing out chlorines. And again, still sp3 hybridized, right? It's just on this one of those orbitals just contains a lone pair. And so now looking at this, so we can compare the angles. And so, right, tetrahedral starts off at 109.5 for all these angles. And then, of course, if you get a lone pair, so it occupies a little bit more space, so then that decreases these angles slightly at 107 for the trigonal pyramidal. And so just so we're on the same page, so what's its electron geometry? Yeah, so tetrahedral, so good, right? Still in that same family. And then what about molecular geometry? What? So trigonal pyramidal. Excellent. So now, right, this is describing the atoms. And so now, let's go on to AX2E2. So which one falls under this category that we've been eager for? Water. So now here's our water. And so this is the classic vent that's usually thought of with our 2 lone pairs. So right, our E2. And right, again, now we have 2 lone pairs, so slightly smaller angle now of that 104.5. Obviously still sp3 hybridized, right? Just 2 orbitals have the lone pair, 2 are involved in bonding. What else do we want to say? And so let's say, so our electron geometry. So what's our electron geometry? So that would be our molecular geometry, right? So that's describing the atoms. Yep, so it's still tetrahedral. So again, base that off of your hybridization. Tetrahedral. Can't spell. Right. Excellent. And of course, right, we could also put like SH2 there as well, so other examples. Selenium dihydride. So let's, I feel like we're going fast through these, but we'll keep going. So now let's do our 5-electron pair. And so this is where the hybrid names, they're just more of a formality. And so now we call this sp3 dehybridized, but really there aren't any d orbitals involved, but we can talk more about this later. So this is just kind of more describing our shape. Sorry, I lost my place here. And so right, sp3d then. So this is, again, just describing our hybrid orbital, kind of the shape that it looks like. And I drew this kind of funky. Let me try that again. So we want to have, so I'll draw it better so that it's more up and down. And then drawing our lobes there. So this is supposed to be 2 lobes kind of on the z-axis, so it can bond, and then kind of looking like our sp2 in the middle there. And so what might be some good examples of this? So starting with AX5. Any guesses? Yeah.
Phosphorus pentachloride.
Yeah, phosphorus pentachloride. So that's always a good example. And so let's just draw that out. So right, our 2 chlorines are on our principal rotation axis here, so our z-axis. And then the other ones are kind of in the center. So drawing this one coming out of the plane of the board, our second chlorine behind the plane of the board. And so this is one where its electron geometry and molecular geometry are the same. And so you can look at your chart. Does anybody know what this is called?
This is trigonal bipyramidal?
Yeah, so trigonal bipyramidal. And so you can kind of see, right, there's 2 pyramids. So that's where the name comes from, one on top, one upside down on bottom. And so, right, again, same answer for both of those, reflecting the structure of its hybrid orbitals. So that looks good. And right, we could have other group 5 examples, you know, of course, like arsenic, pentafluoride, or whatever, you know, antimony, pentabromide, so we could go on and on as well. So those would all fit that same pattern. And so now some of these get harder to think of examples. So let's try the next one. So now we're over here. So right, we did our trigonal bipyramidal. Now we're looking at sawhorse here. Anybody guess an example? Any ideas? So draw the Lewis dot structure for this one. So sulfur tetrafluoride. And then, so you'll find that this one matches. If someone to put SF4 on the board. Yeah, I think go for another round and see other volunteers.
Is this the pivot thing? I guess
Yeah, I try to bring 2-1.
And so, I guess to start with the beginning, we take the valence electrons of the atoms. Sulfur has valence electrons, 6 valence electrons, and then chloride, one has 7 valence electrons, and 4 of them. And that will give us 4 valence electrons for the molecule. And so I started by doing 3 single bonds with the sulfur, the chloride, chlorine, and then I added 1 lone pair in that case, as well as the 3 lone pairs of the fluorine. I guess counting this out, this reagents each have times 4 is 32, and then 2 are 1 lone pair in the giving us 4 valence electrons, and then of course we have valence charge of 4, and then 2 actually sulfur, and then 6 electrons, 1 bond with each of our chlorines, that gives us valence charge 7. Well, that gives us formal charge of 0, which makes them valence electrons. With each group. And I guess to get the shape, we should know parameters and solve this. We would have we would have so it's on the other side of the valence electron, which is the rest of that there. Then the out.
So that looks pretty good. I think Alira did a good job. So everybody got kind of this structure, right? And then you can see, so electron geometry, so we're still in our trigonal bipyramidal, right? And so I like how he was showing it at the end there too, and I try to draw it, so it looks like the playground equipment. You can see why it has that name for its molecular geometry. And you see a few variations of how textbooks call it, yeah.
In the 3D notation, how do we write a double bond?
Wait, you have a double?
I don't have a double bond, but how would we do that theoretically?
I mean, you can still just write like a double bond. Usually you don't put the double bond like on the 3D, I guess is what I'm saying. So like if you had,
But when some chemicals have all double bonds, so you would have to.
but like with, so we saw with SO3, right, that one, it had 3 double bonds, but they were all planar, so we didn't have to draw 3D structures. I guess come up to me with an example where you'd have to draw like a 3D bond. Because I think it usually ends up where you can just put the double bond in the 1D. And so molecular geometry. So again, you might see variations of sawhorse, seesaw, something. So just be aware of that if you read other textbooks. Any questions on this one? And of course, right still, sp3d hybridized, since it's still in the same electron geometry. And so let's look at this next one. So AX3E2, so that gives us a hint. But let's see if we can draw our Lewis dot structure for kind of one of the classic examples. So F4, oh, F3, sorry, F3, my bad. IF3. See what you can come up with for that Lewis dot structure. Does someone want to put our IF3 somewhere on the board for us? We could also erase SO3 up here if we need some space. Yeah. And then, do you want to go for it?
I will.
And then, are you Trenton?
Yes.
Okay. Trying to learn the few new faces.
This is good to the ones on.
Yeah.
We're going here, then your phosphorus can't be to it. And I was left with 2 electron pairs on this. And so I just looking at it, I think I got a T-shape with it. Is that correct?
Yep. so that looks good. And so right there's, of course, you could, count up all your electrons, look at your formal charges. Other ways, right, so you can think of it, iodine has 7 valence electrons, you have 3 involved in bonding, so that left 4, so split up as 2 lone pairs. And so other examples of this are, they tend to be like crazy halogen compounds, so right, like chlorine trifluoride also looks like this. If anyone ever gives you I4, that's what they mean. You can also write this II3 if someone's trying to be nice. But yeah, excellent. So it should look that exactly T-shaped, and you can see, right, kind of why it's T-shaped. It looks like a T. And again, right, we're still sp3d hybridized. So right, we still have our 5 orbitals. You can see that. You can write that if you need to remind yourself. And then, of course, that means that for our electron geometry, that we are still in our trigonal bipyramidal. So that looks good. And so now let's look at our last example in this family. And so that would be AX2E3. And so the classic compound is xenon difluoride. So take a second and draw out your Lewis dot structures. So see if you can figure that out. Does someone want to throw our xenon difluoride on the board?
I'll go for a redemption round.
Redemption round. All right, let's do it.
So well, xenon has its 8 valence electrons, and then you have your 2 fluoride but we can draw 3D. And then got it.
Yeah, that looks excellent. And so that's good, right? You draw the fluorines on the z-axis. We're trying to maximize space between those and then also give the lone pairs plenty of space in the middle. That looks good. So did everybody get that for their structure? And did you say that what the molecular geometry was?
Oh, no, I didn't. I think one thing it just said it was linear.
Yep. And right, so we
But
can
the
see that.
electron geometry is no, it's called trigonal bipyramidal.
Yeah, so we're still on our trigonal bipyramidal. And then again, how Phoenix draw, you can clearly see how we have our linear structure with our lone pairs just occupying that middle area there. So everyone feel good about that? And I'll just write that we're still, right, sp3d hybridized, so still in that geometry. So questions, no questions, feeling okay? All right, so we'll keep speeding through for now. So let's see if we get through all of 6. So now we're on our electron pair 6. So this is formally called sp3d2. So we have kind of our 6 lobes. But again, this is where it gets tricky in the sense that we're not actually invoking d orbitals. So I just like to emphasize that. And any textbook that, again, says that you are invoking d orbitals is incorrect. And we can talk about that at some time if it doesn't come up in lecture. Because I don't think it will come up in lecture, but I'm more than happy to talk with people individually. All right, so then, again, sp3d2. So that means all these orbitals look something like this. We have 2 lobes kind of on our primary axis, and then 4 lobes sticking out in the middle now. And so can anybody think of the classic example that would fall under the AX6 category? No guesses? So there is sulfur hexachloride. So that would be a good example. I was specifically thinking of sulfur hexafluoride only because that's the gas version that people might be more familiar with. But yeah, other variations exist, right? Group 6 plus 6 substituents. We could have other examples. But let's draw, we can draw sulfur hexachloride. And so that's going to be, right, our sulfur. And then this is our octahedral shape, so our parent geometry. So it's both our molecular and our electron geometry. And so I'm just trying to draw it nicely. So again, all our chlorines. So these 4 chlorines are all kind of in a plane. And trying to draw my lone pairs here. So sulfur hexachloride, or you could have drawn the fluoride if you like that one. So let's do, so our electron geometry and molecular geometry. So do we know what this shape is called? Yep, so octahedral. Sorry, spammer's trying to call me. So that's octahedral for both of those. So octahedral. And so again, right, all these group sixes, our electron pair 6, are all going to have our octahedral geometry. So that looks good. And so now let's look at other variations. So take a second to draw out. So we have AX5E, and the classic example of that is bromine pentachloride. So see if you can draw what that structure looks like. Oh, so remember the X's just stand for atoms and E's are the lone pairs. And I neglected Wikipedia after introducing it, but you can see, right, it gives the same information, so you could, again, look at Wikipedia if you kind of like that format better, and it maybe helps clarify what the X's and the E's are, so you can kind of see X's represent where atoms should be, and then we have E's for our lone pairs and all these. Again, you could see that. So I want to put this on the board.
So all chlorines have 7 valence electrons, and bromine has 7 valence electrons. These all combine with single bonds, leaving 2 electron pair on bromine. So that would that would be the electron, sorry about that. The electron structure would be octahedral, and the molecular structure would be square pyramidal.
Yep, so excellent job on the molecular geometry. So writing our electron geometry. Then I still need to copy your structure. So molecular geometry. So you said that was square pyramidal, so that was good. And once I draw it, so I was just trying to copy the octahedral pattern there, and then of course just substituting in the lone pair. And so this is always good practice to draw. And just like he did, right, you may need to modify your structure as you kind of practice and fiddle with it. So it should look just like he drew. So that all looks good. I think we covered everything. And again, still sp3d2 hybridize on those orbitals there. And so again, that's where octahedral electron geometry comes into play. Questions on this one? Feeling okay? So now let's try one of the other xenon compounds. And so this is the abbreviation, so something that follows the AX4, so E2, so something with two lone pairs. And so xenon tetrafluoride now is kind of that classic example. So take a few minutes to draw this Lewis dot structure out, and we'll go over it. All right, who wants to put Andrew Vaughn? Oh, sorry.
For reading questions, I don't know if we're supposed to talk about this later, is that there's a term called ligands.
Oh, ligands, yeah.
Ligands, and I was just curious what those were, what they had to do with this.
So ligands, so this is a good question. So all it means is like things that attach on. And so it's just a term that like inorganic chemists tend to use. And so ligands sometimes also referred to like their labilities, so how they can pop on and off, but just basically things attaching to the metal. So we could even call these chlorines, you could refer to them as ligands, or sometimes they're trying to refer to like a more complex structure. So for example, like benzene can act as a ligand then to iron. And actually, so this is a funny compound to make. So this is iron CP benzene, and so it has both benzene. This is benzene, and this is called CP, which is this structure. So C5H5, where it has this weird resonance here, and then sometimes it has methyl groups, sometimes it has H groups. So this CP, now I've gone on a rant. So yeah, so this is CP, this is CP star. Actually, CP star is more stable, sorry. And this would make like a sandwich compound, so those are ligands. I think last quarter we saw like ammonia acting as a ligand even. And so right, how it can act as a ligand, so going back to its structure, so right, those two lone pairs are primed for donating, especially to a metal, so things like that. CO could be considered a ligand as well. So we briefly talked about CO last quarter, but we can revisit it and talk about how CO bonds by the carbon to metals. So right, there's lots of like nickel, tetracarbonyl. So that this is a toxic compound, by the way, because of the lability of the COs. So actually, this is a great compound. I wanted to use it so badly, and I could not because it's just too toxic. So the problem with nickel CO is it's a really heavy gas. So right, you have your fume hood, and normally you think like your fume hood is enough, but nickel CO is so heavy that it'll just like leak out of your fume hood, and then you'll breathe in the CO, and then the nickel will deposit in your lungs, and that will lead to other horrible things. So yeah, good luck playing with nickel CO. Anyways, I got too excited about ligands. All right, did we draw xenon tetrafluoride out? Does someone other than Alira want to go for it? What about, you haven't heard from like the middle back section? Cora, Camilla, no volunteers? All right. Oh, Carmen, yeah. Yeah, that looks excellent, and I really like the way Carmen drew out the structure with the 3D. So you're right, you can tell that fluorine's coming out, fluorine's behind, and then right, our lone pairs are up and down in the plane. So that was good. And you could draw it probably other ways, you know, kind of flat looking down, but then it might be hard to show where the lone pairs are. So. And of course, right, this is also part of this chapter is, again, drawing in 3D and practicing and all that good stuff. And then did you say what the geometry was?
The electron geometry would be octaedral. The molecular, I don't know the name. Was it square planar?
Yep, that's an excellent. So right, it looks like square planar, so it is. Right, chemists aren't too crazy with naming. So yeah, square planar. Wow, we really flew through that first half. All right, that's probably a good place to end for today just because I don't want to get into the other topics. So we'll pick up on Thursday with our isomers, so we'll look at isomers and all that. All right, so you get a little break early, and then I'll see half of you in lab today.